We spent last class and the last lesson talking about the basic exponential function f of x equals, or y equals, a times b to the x power, where a is the initial value and b is the factor, base, or common ratio. But today we're going to get more detailed about the types of increasing or decreasing graphs we can have in the world by talking about what's called exponential growth and exponential decay. Now, based on those words and the way that they're spelled on this page, with growth getting bigger and decay getting smaller, you can kind of tell that these are going to be our two increasing and decreasing functions. Okay, the function a times b to the t is getting more details. That's what I'm going to kind of call this. We still know that the part that's in the parentheses, okay, that's highlighted right there, is still going to be my constant ratio, but when it's going to describe exponential growth or exponential decay, we're actually going to call it the growth factor. Okay, because that's the factor we're multiplying by to watch this function grow. It is still the constant ratio, it is still the base, but that entire parentheses has now got some details in it. The details that are inside of this include the fact that we are talking about r, which is now going to be the rate of growth. Okay? Now, this rate of growth is always going to be in a decimal form when you put it into the exponential growth or decay problem. I'm going to give them to you as percentages, but you're going to have to use the Dr. Pepper rule to move it back into decimal form. One thing I want you to notice that's a big difference between these growth and decay functions is that the growth function in the details inside that b parentheses, you're going to see a plus sign. So this number that we're multiplying by is going to be bigger than 1. That means that it's growing. And if we look down at the decay equation, it's got a negative sign, which means it's going to be less than 1. So we're subtracting that now, what we call, instead of rate of growth, rate of decay, that is still in a decimal form, from 1 to show me my actual decay factor. So really what we're doing is we're still working with this equation right here. However, we're just going to give more details to the constant ratio. We're going to understand if it's a growth factor, so the equation would be going uphill, a curve that goes up, or if it's going to be a decay factor, so the curve decays or goes down, is decreasing. So really, again, we're just giving more details today to the b, and these details are going to allow us to understand why we really study these functions in real life. We're going to be using a lot of real-world scenarios here, ways in which you actually see exponential growth or exponential decay. Now, before we get into those, real-world situations, we got to make sure we understand the idea of growth rate as compared to constant ratio. So we're going to identify the function given as growth or decay. Remember, growth, again, is going to be our increasing functions, increasing curves, and decay is going to be our decreasing curves. Then we're going to sketch the function. We're just going to give it a good sketch. We're not going to plot points and make it perfect. Then we're going to identify the initial amount A and the rate of growth, rate being the percentages of growth or decay. All right, our first little bit right here, we have f of t equal to 475 times 0.45 to the t power. Easily enough, and this doesn't change from last time to this time, we know that 475 is going to be my initial value. I'm just going to pick a random point on here, say, guys, that's 475. Great. I know that that is the a value. That is where my graph is going to begin. Since the b value right here is less than 1, b value being less than 1, that means I would have had to subtract, and that this is a decay function. That means that this is going to be a decreasing function. Remember, it doesn't cross or touch the x-axis because of the asymptote there. And that my b value is 0.45. Now remember, I did not ask you for the blue b value or the factor, I asked you for the rate. So we're actually going to have to do some math here. We're going to have to actually figure out what I subtracted from 1 to get 0.45. what do you have to subtract from 1 to get 0.45? Yeah, if you subtract 0.55 from 1, you're going to end up with 0.45, which means that my rate of decay is 55%. That's my R value, 55%. Okay, remember I want to be able to talk about the rates as percentages. That's what we do in like real life, we talk about them in percentages. But in the equation itself, it does need to be a decimal, so you'll move that decimal point 2 times. Now I've got one for you to try. Again, this should kind of make sense from what we did last time. Pause the video right now, try to sketch this function with its initial value and whether it's going to be growth or decay, and see if you can fill out some of the A and B and R for this function. Go ahead and pause the video. Again, feel free to laugh at my wobbly curves here, but you should have noticed that this has an initial value of 12, so we're going to start at 12. We'll say that's 12. And since the B value is bigger than 1, we would have had to add to create this B value. So we know that this is going to be an increasing or a growth function. Now, of course, 1.05 is my B, which is the growth factor. But if I want the rate, I'm going to have to do this math to figure out what I had to add to 1 to get 1.05. And hopefully it's pretty obvious that you had to add 0.05 to get 1.05. Now, what percentage is that? How do you change 0.05 into a percent? I remember the Dr. Pepper rule tells me that I move dp 2 spots to the right to create a percent, and this would be 5%. So we have growth and we have decay functions. Let's talk about what these look like in real life. Okay, we're going to write some equations for some situations right here using that function a times b to the t. Here's what we're told. In 2005, there were 100 rabbits in Polygon Park. The population increased by 11% each year. Okay, I'm going to highlight some things I know. It says there were 100 rabbits basically to begin with or initially in Polygon Park. That's going to be my A value. Then it tells me that the population increased by 11%. When you get a percentage, you know that that is the R value that you're going to use. Increased means that this is going to be a growth function. So when I use the details of this function, I'm going to have to put a plus sign. So I'm going to be trying to fill out f of t is equal to a times b to the t, but I know that b is going to be 1 plus the R value, because we're going to be increasing. Okay, that's pretty easy. Let's plug the things in where they belong. We know that the initial value is 100, and we know that the rate is 11%. Now, I'm not going to put a big old 11 right here, because I have to make sure that that's a decimal. To change 11% to a decimal, I'm going to move its decimal point 2 times to the left and get 0.11 as my decimal for that percentage. Now that I've put in the rate, the only thing we have to do to like finish writing this is in a times b to the x like form is just add or subtract whatever's inside that parentheses. And 1 plus 0.11 is 1.11. So this right here, f of t, is my a times b to the x with my constant, or with my growth factor showing. Okay, so I go from the details of the plus or minus with the rate to the entire number so that it's now b instead of 1 plus r. Number 4 is pretty much exactly the same thing. It says a $900 sound system decreases in value by 29% each year. Okay, this is how much the sound system was worth, which is way too expensive for a sound system in my opinion, but to each their own. And we know that this is going to decrease in value by 29%. Percentages are my rates, which means they've given me R, not B. So I know that I'm now going to have to fill in the decay function. So I have the details on the inside of this function, but this time I'm decreasing, so I'm going to subtract. All right, we know that the not expensive $900 sound system, it's way too expensive for a sound system. And then we're gonna have 1 minus 29%, but I'm gonna write that as a decimal, so what number would I put in there? 0.29 is the decimal version of 29%. And just to finish this up, all I need to do is simplify that parentheses, like do that subtraction or addition no matter what it is. 1 minus 0.29 is 0.71. If you don't trust me, consult a calculator. And that is a times b to the t power that represents the depreciation, or how much it's worth later on. So these are really cool. These sorts of functions explain why like rabbits are exponentially growing in population when they take over parks and stuff, and why when you buy something technology-wise and you try to sell it back in a couple years, that it's not worth the same amount because they depreciate exponentially over time. Okay, let's make sure we understand a little bit more about the parts of these equations. So this time I'm going to give you the equation and we have to figure out some stuff about the equation. Number 5 says Penelope opened a bank account where she can earn compound interest. This is like a real thing in real life, okay? The initial deposit was put into the account and no additional deposits or withdrawals were ever made. The balance in her account can be modeled by the function S of t equal to 500 times 1.015 to the t power, where t represents years. Now, if you notice, this is already in a times b to the t power. So we already know what our a and our b is. So let's read some of our questions. It says the initial balance in the account. Well, that's easy. Initially, we had $500 in this account. Good job, Penelope. You're saving at least $500. And now, since b is bigger than 1, since this is bigger than 1, is this going to be increasing or decreasing over time? Increasing. It's a growth equation. This is what happens when you save your money in banks. The next question, though, asks me for the rate which the balance changes each year. Remember, the rate is not the same thing as the b. I'm trying to figure out what 1 plus the rate is equal to 1. Words are really hard today. 1.015. Now, growth is a little bit easier. Pretty obviously, I had to add 0.015 to 1 to make that equation make sense. So the rate that I use every year is 1.5%. because I'm moving that decimal twice. And now the next part says the balance in the account at the end of 3 years is. Well, they've given me 3 years. Okay, that's what they're telling me here. I want to figure out how much money Penelope has saved if she leaves that money in the account for 3 years. So we're trying to figure out what the balance in the account is after 3 years. We're going to plug in a 3. So we have 500 times 1.015 raised to the third power. We're going to plug and chug that into a calculator, and we would see that the amount in her account after not touching it for 3 years has grown to $522.84. All I did was plug this entire thing that doesn't have any exponents or any variables left into a calculator like Desmos, and it will calculate the output for me. So again, this function right here actually contains a lot of information. Definitely tells me how much I started with. It will tell me if I'm growing or decaying, and the details of this number will tell me what the rate is that I'm using to grow or decay each year or every time. Let's check out number 6, last problem. 2 years ago, Antonio bought a new iPhone. He now wants to sell the iPhone for what it's worth so he can upgrade. Classic, that happens all the time. The iPhone's value can be modeled by the function p of x is equal to $725.99 times 0.4 raised to the x power, where x represents years. This information was accurate as of 2019, so this was probably the iPhone 8 price. I know we're at like 10 or 12 or I don't even know what number we're on. They're way more expensive now, but we're just going to trust this, okay? Again, this is already given to me in a times b to the t power. So we already know what the initial value of this phone was. Antonio paid $725.99 for his iPhone. That's the price of an iPhone in 2019. And the value of this phone, is it going to increase or decrease over time? Now, logically, we know this as well as the equation tells us. The B value is less than 1, which means it's going to be a decay function. Plus, if you try to sell back an iPhone later, you're never going to sell it for the amount you bought it. It's going to be worth less. It's going to decay or depreciate. Now, finding the rate that this phone can sell for after a few years, again, the rate is a percentage. We need to know what 1 minus something is equal to 0.04. What would I have to subtract from 1 to get 0.04? Yeah, I'd have to subtract 0.6. So the rate at which this phone changes or depreciates each year is 60%, moving that decimal twice. Okay, so we are Antonio right now, and we are trying to sell our phone back after the end of 2 years because we want to upgrade, right? So that means that we are going to figure out what the price of this phone is in 2 years. We're going to plug in a 2 to the original equation we were given for this phone. We're going to see how much this phone is worth in 2 years. So if you bought a phone in 2019 and you were trying to sell it right now in 2021, and you had whatever iPhone this was, iPhone 8, I guess, and you figured out how much this would cost and you sold it for what it was worth, the most you would really get is $116.16. If you waited a third year to sell it back, if you waited till 2022 to sell your iPhone, it would be worth like $46. Technology depreciates over time, so when you make investments with your money later, you need to make sure you're making good investments, and that's where this function comes in. So this is actually pretty cool and something you definitely need to understand, or else you'll get fooled into buying stuff that you don't need, don't want, can't afford later on in life. Okay, again, this is exponential growth and decay. It's really just the details of your A times B to the X equation. Growth is a positive R, 1 plus R. Decay, you're subtracting, 1 minus R. We're going to be writing equations and talking about scenarios in class, so we will see you soon.